Hey guys, welcome back to another episode of Simuleos. Just checking my camera, everything seems good. Okay, so here's the thing guys. Outside today, there is apparently supposed to be a tropical depression or something like that. I'm not sure, I don't think it's a typhoon, but I'm not hearing any wind or anything, so I think we're set. It might be coming tomorrow. I might be wrong about that. So if it is coming today, if it is technically outside, I will probably close the stream if and only if things become too noisy for basically me to hear myself speak. Outside of that, I think it should be okay. I don't know if you guys remember, but if you were here last year, every once in a while there were these, crazy typhoons that would come through, and when they came through, it just was so loud. Like the windows were just like screaming, and there was no way for me to do a stream just because there was just too much noise outside. But it seems perfectly fine. I'm not hearing anything right now. Maybe whatever it is just passed last night and I didn't even notice. But really, it's not even a big thing. It's probably not even a Category 1 typhoon or whatever they're called. So just letting you know that if something does come up like that, it might, but probably not. Outside of that, last night, Gustorn submitted a pull request. Very glad he did. Let's go ahead and take a look at that. So if we go here to the pull request, let's see, where are we? Wait, what am I doing? Let me just go to this, Leos Simuleos. And then let me do the last pull request. Here we are here. And let me see, latest commit, that one. Okay, so basically what happened here, if you remember from last time, we had, it was like half an hour ago. Oh, my bad. I just woke up, so like anything for the past 8 hours could have been whenever, I don't know. So while I was sleeping, Gustorn submitted a pull request. So as you guys remember, last time when we were outputting particle data, we had a bit of a problem. Basically, we were outputting the particle data of each of the leaves of the Octree. However, when we were updating the particle locations, we were updating only the locations from one node in particular. The easy way to fix this problem was to change everything into pointers. So change all of the all of the vectors that I had in every single one of the how do I put it? Every single one of the nodes, and then we can go from there. Hey, Akira 88 Spark, 1 second. You were outputting center masses, not particles. I fixed that too. Did we want to output center masses? 1 second, let me think. Let me see how you output the particles. I'll check that in just a second. But basically the idea here is that we are now outputting, what am I thinking here? We now have pointers, and that's good because this means that all the data is being mixed or kind of mixed between all the different nodes. So now this is incredibly useful, and if we update the position of one particle, it's updated in all the particles underneath. Now let me check something. We have current PVEC. Where am I doing the center mass thing? What I wanted to do, PVEC here, particle. Where's my center mass stuff? Here it is. PVEC 0. Yeah, that works too. Same thing. Good. Because in the end, the way I see it is if you have a center of mass, but there's only one particle, the center of mass has to be that particle location, right? That was what I was going off of. Regardless, doesn't matter. Seems good to me, so let's go ahead. Wait, let me think. Actually, yeah, this is fine for now. There is a situation later on down the road where we need output center mass instead, but that's fine, it's not for now. Okay, so what are we gonna do? Let's go ahead and go over here and let me run into CD Projects, Simuleos, and of course, Barnes Hut. 88 Spark, can you show your math books? Let me see really quick. Give me just a minute. Okay, so I'll be honest, most of my books are in this footlocker that I have just over here, and it's kind of hard to get into right now because I have a whole bunch of stuff on top of it. But I don't really have that many math books, really. Most of them are physics books. So one book that I go through a lot is Griffith's Electrodynamics. This is the 3rd edition. I don't think it matters which edition you go through, but it's got a good bit of vector calculus and stuff that you need at the very start. That's incredibly useful. Another book that I use a lot is Thermal Physics by Schroeder. Incredibly useful. It goes through a lot of the statistics and stuff that you need, so information theory and stuff like that. Sorry, that was loud. Another book that I've got that isn't, that I don't go through that much, but I do go through when I need a reference, is Numerical Recipes. A lot of people use it as a good reference book, but unfortunately because of the licensing, it ends up being that if I want to use the code in this book, I've got to, like, basically give the code to these people. Like, the licensing is really weird. So basically I just use it as a reference, and then I kind of make my code from there. Hey, Maximilian Lloyd. So those are the only books I have out right now because those are the ones I was looking at. But I have a couple others that I use a good bit. Namely, let me see, Quantum Mechanics by, what is it? It's Quantum Something by Griffiths again. And then there's this Introduction to Plasma Physics by something and Bhattacharjee. I don't remember the first guy's name. If you're interested, I can give you that. Unfortunately, I don't have any of my calculus books with me. When I moved to Japan, I kind of left a few books behind. But it's some of those books are incredibly useful. For example, Griffith's Electrodynamics, a lot of people use a lot. Schroeder's Thermal Physics, I find incredibly enjoyable and fun. However, a lot of people think otherwise, so keep that in mind. So, it's really slow. Alright, I'll take a look at that too. So CD into projects, Barnes Hut. Okay, one thing I have not done yet today, Simuleos and then Barnes Hut. I've not described the problem that we're working on. So, if you don't mind giving me just a minute to talk about the problem, and then we'll go from there. So Zernal, here. Enter. Okay, so let's talk about what we're doing. What we're doing is we're generating something known, or we're using something known as the Barnes Hut algorithm. Now, the Barnes Hut algorithm is basically a way for us to do an n-body simulation, where the n-body simulation is basically, how do I put this? It allows us to do as many particles as we want. Now, if it's very slow, that means we're doing something wrong, and I'm not sure exactly what we're doing wrong. So we have to think, I have to think about that. Because technically, we should be able to do as many as we want by ramping up that theta value. So let's see what we can do. So n-body simulation here. The idea is that we have, let's say, a box. In our simulations, we'll have a cube, but here I'm just going to do a box. We have a whole bunch of random particles in the box. And what we do is we continually split up the random particles, something like this, into quarters, or in the case of a three-dimensional box, octants. So it's often called an octree code. We continually split up this box over and over, and over and over and over and over again, until, one second, all of the particles are in exactly one box, if that makes sense. So like, all of the boxes have exactly one particle in them. Something like this. Okay? Yeah, we'll check. There's a whole bunch of things to check. So basically what we're going to do then is after splitting up the box, which I'm doing right now, let's say this particle's over here. And again, forgive me, I'm not very good at drawing, so if I was a little bit better at drawing, this would be a little bit easier. But basically the idea is we have a whole bunch of different boxes here, right? We have the big root box, which has everything in it. And then inside of that, we have a whole bunch of smaller boxes. So 1, 2, 3, 4, being 1, 2, 3, 4. Here, we can even do it this way. So we have a big blue outside box. Something like this. I'm kind of squiggling, trying to make it a little bit, you know, more obvious. Then we have 4 red inside boxes here. We then have, let's see, another 4 here. Another 4 here. Another 4 here. Another 4 here. And then these are split up one more time, and in some cases 2 more times. So we have another 4 here, 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 here and here, here and there, And then finally split up one more time, which I'll do in pink here and here. Okay, so if I were to draw this out, it would look something like this. We have some big blue out here. Then we have red, 1, 2, 3, 4, splitting off into green, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Let's see here. So we have, best way to do this, I suppose, would be to have 2 nodes here, 4 nodes here, 0 nodes there, and 2 nodes here, something like that. Oh, 3 nodes there. Okay. And then 2 of these guys are split up even further. So we have 1, 2, 3, 4, 1, 2, 3, 4 into these nodes here. Okay. Now, some of these guys have particles in them. Some others of them do not. So you have to kind of keep track of that. So I guess what I'll do there is the following. So I'll say, let me see. This one obviously has particles in it. This one has particles in it. This one has particles in it. 1 second. Over here we have, 1 second. Particles. Particles. I'm just kind of randomly filling these guys. And I missed a couple, apparently. Oh shoot, I missed the blue boxes. Anyway, the point is, we can represent all of these particles as trees. And that's kind of what we're doing here. I missed the blue boxes. I apologize for that, guys. But I'm hoping this is coming across. If it's not, feel free to ask a question, and I'll totally get to them as soon as I see them in chat. But the idea, again, is that we're representing this spatial grid as some sort of tree. And we're saying, okay, where are the particles? They are either in a box or they're like, where are the particles based on these boxes? And that's kind of how it works. Again, I apologize. That was kind of a shoddy description, but I think I kind of got the point across. The point is, we've already done a couple of things. We've already put in the octree. That one was set. Now, as of last night or yesterday, Flood from Nowhere, I just started 13 minutes ago. So thanks for coming in. Okay, so we have octree here. This has been implemented. We're good with that. Then we did our RK4 algorithm. This guy has been implemented, kind of. We're working on that today, going to finish it up. Okay, so now we have to worry about visualization and stuff like that. And what we need to do for visualization is going to get really messy really quick if we have to move into visualization. Right now we're using NuPlot, but we need to change this into OpenGL or something that we can do more real-time things with. So this is going to be a little bit rough when we start moving on to this, mainly because my understanding of OpenGL is quite poor right now, and I need to kind of get it a little bit better. So we're going to kind of go through what I know so far, and where we need to go in order to get to what we need to do, if that makes sense. So we'll kind of be learning that as we go along, but that's okay. I think that's good. We'll kind of treat the OpenGL as if it were its own simulation, and kind of go from there. So, visualization, that's the next step. A few other steps that we had to do along the way. Again, Gus Torn submitted a pull request a few minutes ago, 30 minutes ago, I guess, maybe an hour ago. And that pull request basically changed all of our position vectors into, or all of our particle vectors into particle star vectors. So these are now pointers to the same particle vector, and that's great. Because now we can basically update a single particle, and it updates that particle along the entire tree. And I think that's about all I need to do for the introduction here. I've introduced what an octree is. Oh, the last thing I need to say. I see. This is one thing I totally forgot. So let's say we have an octree. Let me go back to the previous one we had before. The reason we want to do this is rather interesting. So let's say we want to tell all the forces that are enacting on this particle right here. Okay? Well, on the one hand, we could do this by literally taking into account every single individual particle that's coming towards this guy over here, right? However, if we have millions of particles, this is potentially hard to do. But what we can also do is we can assume that all the particles over here act as one big center of mass. So instead of calculating 1, 2, 3, 4, 5, 6 particles, we calculate only one. And this allows us to cut down the compute time. The reason we're allowed to do this is basically because the Yes, actually, we can't exactly, well, not exactly, but we can definitely model our solar system or something like that. What we're intending to do here is basically do some sort of gravity simulator. So, for example, the force that this guy feels from that guy over there is going to be F equals G times the mass of the center of mass of those guys over R squared times its own individual mass. So it's going to be GMM over R squared. That's going to be the force that it feels. So you could imagine some sort of orbiting or something like that. In general, we see these simulations done for very large scale n-body simulations. However, I'm not sure how it's going to work. So we're going to see how far we get. Main thing is we've already implemented most of this stuff. We're kind of on the last step here. But it's definitely used a lot for any type of planetary bodies or things like that. Now, what do I want to say? Okay, so that's kind of what we're moving on to here. How do we know that we can represent all of the mass as a center mass? Well, what we do is we create this value called theta. Now, a lot of people call it different things. I'm just going to call it theta. And we say that the theta is going to be equal to S, which is going to be the radius over here, over D. Here. So we're going to say it's S over D. And it might actually be this entire length here for S. So S, D. And I realize this is kind of a messy plot, but hopefully you can still follow it. And the idea is that basically the farther away we are, the lower the theta value is, and the smaller these guys can be represented, like the smaller the radius of this clump of particles, the lower the theta value. And this theta is a threshold, right? So if we are above this threshold, we count every particle as its own entity. But if we are below this threshold, we count all of the particles within that branch of the octree, so something like this branch right here, as a single particle. So we can effectively ignore all the particles underneath here and only deal with the center of mass up here, if that makes sense. I found a bug in my way, line 252, you need to change current to current center mass particle. Okay, I will do that. Okay, so now let me go ahead and get started with the code. But first, let me pause really quickly for questions, because I did kind of go through this quickly. So if you have questions, comments, concerns, anything like that, go ahead and let me know. I'm going to get a quick sip of water, and then we'll go ahead and get started. Okay. This is going to be interesting. I don't know why, I got plenty of sleep last night, but now I'm like super groggy. I don't know. I don't know what it is. Like if I get 6 hours of sleep, I wake up and I'm perfectly fine. You know, I'm not happy, but I'm fine. You know? When I get 8 hours of sleep, I just wake up and I'm just not able to do anything. I'm just like completely out of it. And I did, I think, get 8 hours of sleep. I went to bed at actually like 8:30 last night, and I got up at around 4:45, so technically more than 8 hours, but it was kind of restless sleep. You know, I was up and out. Okay, so let's go ahead and do a git pull. I think I just do git pull. And these are pulling the change merge request basically given to us by Gustorn. Now let's go into barnshut.cpp and let's change 252. Okay, so we have vector current P to current center mass P. Okay, done. Now let's go ahead and make this and see what happens. Let's go here, make. Okay, so it looks like everything was put into particle check.dat. Let me see what's in that. VI particle check.dat. Looks to me like we have 2 different time steps, and let's see what happens. So let's go ahead and write quit. VI new plot. Oh, what am I doing that? New plot. Exclamation mark new. There we go. I don't have anything here, so let's just plot particle check.dat. We'll say I0. This is the very first. Oh. Splot. This will be a 3-dimensional plot. Okay, so here's where all the particles start. And here's where they all go. Okay, so let's see what happens if we plot them together. I0. And then we're going to go over here. Do I... 1 second, replot. And I1. Okay, so you can see them all kind of moving. Some of the particles are shot out over here. And let's increase the size of this window so it's a little bit easier to see. Oh, hey ZZ, hey, what's up? Let me know if I missed any questions or something you had while you were connecting. Sometimes it takes a while. But yeah, so here, the purple particles are where we start. The green is where we go to. And you can clearly see some of the particles over here are shot out, but that's okay. The one thing I'm a little bit worried about is the fact that they're all kind of moving towards this one plane. I'm not sure exactly why, so that might be an issue, but we'll worry about that as we come to it. Okay, so now let's check something else. It should be that as we output all the particles, we should have this other file called pout.dat. And pout.dat should now basically give us the same thing. So let's go to pout.dat. I0. So this is the first time step. And now let's output particle check.dat. Oh, okay, those are two different, that's different data. That is definitely different data. So here is particle check, and here is pout. Let's go to replot. Yeah, that is totally different data. Completely different. So this is something I'm gonna have to think about. I think it should be the same data. So let's go through and let's check this out. So what are we gonna do? Let's go through and just kind of look at the code real quick and see what needs to be done. So let's go up to main. Okay, so what do we have here? We have, we're defining our file for output. That should be fine. We're creating our vector of particles, and we are generating our octree with pvec. Now, one thing that was changed, let me go into Control T, which I'm very glad was. Let's go into barnshut.h. Now when we initialize our, let me see, node over here, we can initialize it with, simply the pvec. Where is it? Node here. Vector location double length. 1 second. Divide octree node root make octree. Oh, here it is. Make octree. I found another bug on vec.h line 77. Let's go to that. vi vec.h line 77. Return left hand side, right hand side. This is pretty big. Last addition to multiplication. Oh, yes. There we go. Vector left hand side, right hand side. Okay, looks good. Right, quit. Let's make that. And let's go into new plot one more time. Sorry for the yawn, guys. Again, if you guys have any questions or anything like that, let me know. Here's the initial particles. Here's the last replot. Here's where they go to. They still go to a line. I thought maybe that would fix that. Okay. Control D. Now let's see if we can figure out why we're not outputting everything. Okay, I see why. So both particle outputs are... Oh, you changed how particle output does its thing. Oh, no you didn't. Oh, I see. They should literally be outputting the same thing. Here, let me go ahead and do this. Remove star.dat. Okay. Now let's do make one more time. 1 second, make clean. Then we're gonna make. Okay. So now it should be, because we're doing particle output basically twice, with the same root node, it should be that these are exactly the same. So let's do... Yeah, I just realized that. So they should be exactly the same. So let me go into new plot one more time. And let's go ahead and plot particle check IO. So this is what is output in cout. Okay. Now let's go over here and let's output pout.dat I0. Okay, now they're the same. I don't know what happened before. Now they're the same. That's good. Okay, so now let's output over here. Let's replot. 1 second. Replot. I1. Oh. Well, those are the same too now. Let's do pout. I1. 1 second. Those are also the same. Okay, wait. Something weird is happening. Let me go check some of the data. So let's go over here. Let's do vi pout.dat. Okay, let's scroll down and see if we've got... Yep, we do have another index, but for some reason they're the same particles. Negative 4.486765. After force integrate, they should be different, but they're not. So let's go here, quit that, and let's check particle output.dat. Particle check.dat. Negative 48675. Good. 48675. Okay. So, we got to think about this one a little bit. Go ahead and quit here. And let's see what's happening. So let's go down to force integrate. Could be the time step. Maybe if we increase the time step. Let's open up the file one more time. Okay, looks to me, yeah. I thought maybe we just didn't go far enough down, but looks to me like we did, no problem. So let's go ahead and quit this. And let's figure out why they aren't moving. So it could be a number of things. It could be that the mass isn't high enough. It could be that they are actually changing, but they're changing by something times 10 to the negative 32nd. So, you know, it doesn't really matter that much. Let me see, make octree, divide octree. Let's go down to force integrate. I swear it was just working a second ago. However, that could have been a bug. So let me see. Basically what we have here is a couple of different functions. We have RK search, which basically goes through and does a depth first search of our tree and changes the acceleration of all the particles. Then we have another one, which does RK4, which does the actual force integration. Now, one thing I want to point out, theta 2 less than theta, is that we do read in a theta somewhere. Where do we read in the theta? Oh, the theta value is up top. Okay. So we got to think about what's happening here. So right now we're just assuming that there's a constant acceleration. However, that's going to change today. All right, Gastron knows why it doesn't work. By the way, guys, so yesterday I was on r/Twitch, you know, reddit.com r/Twitch. And there was this guy who was mentioning that he wants to be... That's okay, Gaston. There's this guy who was mentioning he wants to be the Bob Ross of video games. And I guess I just want to know your guys' opinion on that. So for me, I thought that was really weird because I think to myself, okay, you know, I like Bob Ross. He's a cool guy. I mean, maybe I'm not as into him as a lot of other people on Twitch are. I really like him. But what does it mean to be the Bob Ross of video games? Like, for example, let's say you want to be the Einstein of video games, or the Maxwell or Tesla of, I don't know, painting. It doesn't really make that much sense. In some sense, maybe it does, but I don't know. I was wondering, what do you guys think about people emulating specifically Bob Ross, but other people, and trying to recreate their style in other media? Like, I guess I found it a little bit weird, and I thought maybe I wasn't the only one, but maybe you guys totally agree. There's a way to be, you know, a Bob Ross for video games. The way I see it is, you know, Bob Ross does a lot of creative stuff. You know, he does a lot of painting and stuff like that. So if you want to be the Bob Ross of video game, you'd have to be a heck of a game developer, and just like every day developing a new indie game or something like that, or a new aspect to an indie game or something. Couldn't quite figure it out. Okay, so why isn't this working? Let's go through and check this out. So we have our octree output. Let's go down to force integrate. Here. Oh, oops. Force underscore. There we go. So this has to be in either RK search or RK4. I'm not sure where the issue would be. So what I want to do here, you can't make sense of Bob Ross, is it? Yeah. I mean, he's super popular on Twitch. So we're changing the particle position and we're changing the particle velocity. Yeah, I don't know. It's weird. So we have the position changing. We have the velocity changing. But it's obviously not changing enough. So let me just try a couple of different things. First, I want to go up to main, and I want to try increasing the time step. Acceleration is always 0 for a lot of particles. What if we just do it twice? Let's try that. Let's go here, Control D, make. Check the particles. So we're going to go to, let's go into VI particle check.dat. Starts at negative 486, goes down to negative 48674. Oh, those did change. 48675. Yeah. Let me try something. Let's increase the time step here. Control D. Oh, what was I? I don't know what I was thinking I was in, but clearly. Okay, so let's go over here, and now let's run it. Actually, it did just run. So now let's go to new plot. Okay, and what do I want to do? I want to say, Oh. Where's the last plot? Here it is. There's I1. Let's plot I0. Okay. Here, they... Huh. Here, let me make this a little bit bigger so you can see what's happening. Okay. So, this is a little weird to me. I'm not sure exactly what's happening here. Some of the particles are being plot. We're never accelerating, we're never updating the acceleration of particles that are close enough. Okay, so let's go through and let's take a look. So it's going to be an RK search. Here we are. Next one down here. Okay, so what's happening here? We are saying the particle acceleration is going to be, okay, plus equals d times, so that should be fine. We're never updating the acceleration of particles that are close enough. Okay, so what are we doing here? We create some sort of vector d, which is a distance from the center of mass of the particle that we're currently looking at, and the particle that we are currently coming from. So we have two particles, particle A, particle B. Distance between those two particles is d. Then we say we have inverse r, which is going to be the inverse of that distance. I don't know why I changed it to inverse r. Should have been inverse d, but that's okay. We have theta 2, which is going to be basically our cutoff. So we ask, hey, are we supposed to check this particle or not? And this is based on that theta value we said before, right? So if theta is incredibly low, we don't check it. If it's high, we do. It does look to me like we definitely, it looks to me like we go through all the particles. Yeah, it does kind of. Because it looks like we're going through all the particles in the original p vector. And then we go from there. Okay. Now let's go down to RK4 real quick. Now, there has to be something going on though. So let's plot the first time step here. And let's go down and plot the original time step. What if we're outputting everything twice? Let me see. Let's... Maybe we're outputting everything twice. Let me go into VI. And let's just go to pout.dat. Okay. Let's see, it's 202 lines. Let's go to set number. And let me scroll down. We should have, yeah, so at about 100 here, about 200 there. Now let me go into, quit here, particle check.dat. And let me see, this guy has 808 lines. One thing we should do is skip RK search when current equals particle. Yeah, we should definitely do that. Let me go up here. 1 second. If current not equal to particle. Here we go. Okay, so there's something weird going on with particle check.dat. Apparently we're outputting more data than I anticipated. So let's go down a little bit. Okay, so that is, let me do set number. At line 100, oh, I bet you, is it because we're just appending to the data? Maybe that's it. So let's go ahead and do rm particle check.dat. Now let's run Barnes Hut. Oh, here, let me just control D. Barnes Hut. Okay, now let me go into particle. Oh, oops. Particle check. What was it? Particle check.dat? I think it's what it was. Now we go into particle check. Okay, I now see what happened. So basically what ended up happening was, here, let's run this one more time. And now let me go into particle check.dat. Yeah, okay. So we kept appending to this file instead of rewriting the file every time. And if we were to rewrite the file every time, I don't think we would have seen the same bug that we saw before. Now what we're going to do is go into the make file, and let's change this so that we overwrite the file every time. And this should fix the problem that we had before. However, had we plotted the particle output instead of the particle check, where particle check was just basically us taking whatever was output to the terminal, if we would have taken the particle data, p out dot dat, it would have been okay. So let's go into make one more time. Current not equal to particle. Current was never declared. That's fair enough. Let's go up here. Where are we? Root, node root, RK search. 1 second. If not current, if current, oh, I guess this is just going through root. So I guess this is just root not equals particle. Oops. Oops, I did it again. There we go. Let's go make. Part was not declared in the scope. Pointer types node and particle star. 1 second. Yeah, I don't know what I'm thinking. Let me just remove this. Okay, so let's just do this then right here. Turn on my air conditioning because it's getting a little bit hot. And then let's go down here. RK search is here. What are we doing? Theta here. What do we want to do? We're saying... Wait, Gustorm, what you wanted to do was skip RK search when current is equal to the particle. Okay? What are we doing here? We're going through all the particles. And what we want to say... Again, sorry for the yawn, guys. Is that the node current... So current particle... That was simplified? Yeah, so you want to do the current here. So something like... If... let's say current pointing to particle equals particle. Oh wait, what? If current pvec.size equals 1 and current pvec 0 equals particle. 1 second, are we updating? 1 second, let me think. So we're going through all the particles up here. And we have root pvec. So we're going through all the particles in our particle vector, right? We do an RK search. Okay? So then we're checking. Let's see. We're checking root. Wait. 1 second. I have to think about how this works. We're going through all the particles in pvec, and we're finding a new acceleration. Okay? So node current. In this case, it's going to be root, and we're just going through everything else. Now, do we do an RK search after this? Or is it only called there? Oh, obviously. My bad, I hit the microphone. It's recursive. So then after checking all the particles in root pvec, we then search again. I see. So we're going through every single particle. And then from every single particle, we're going through the entire tree over and over and over again until we found... Okay, I see, fair enough. Okay, so if we are... If the node currently has 1 particle... Yeah, okay, sure, fair enough. Okay, so let's go here. Current pointing to pvec, which... Yeah, dot size equals 1. Ampersands, current... dot pvec of 0 equals particle. Then we're going to say, I guess return. 1 second. Yeah, let's just do return. Also, another thing about it, we shouldn't call RK search in a loop. Why not? 1 second. Yeah, maybe there's another way to do it. Let's just return this. Write this, go over here. Let's make it. Pvec 0. 1 second. That needs to be an arrow. Like this. Go over here. Make. Current pvec.size. I forgot parentheses. Let's go here to make. Okay. So now let me just very quickly go to new plot again, and let me show you that now we should have everything fixed. So let's go ahead and splot pout.dat I0. Okay, so here we have these guys here. That's the very first time step. This is when we initially create everything. Then let's go down here and replot it with I1. So let's do pout.dat I1. So this is the next time step. And you'll see that everything is very slightly shifted, which is exactly what we want to see. So this means that we are seeing all the particles kind of move together towards their conglomerative center of mass, or their, I guess, center of mass together. And that's good. So we are seeing the particles kind of sort of move forward. Now, let's go through and let me check one more thing. I want to go up to the top. Actually, I just want to go up to main. I want to output a couple of different time steps. So let's do the following. We're going to say up here, 4. Let's just do 5 time steps or something like that. So we're going to say 4, I equals 0. That was meant to be a 0. I less than 5. Plus I. Okay, so now we're going to say, first we output all the particle stuff, and then we go from there. So we're going to do this. Okay, we do the new lines. Something like this. Good. And then we do force integrate. So we're going to do force integrate. And we just move it forward 1 time step. So we're going to say root 0.01. Then we are good to go. So let's go ahead and remove these guys. I'm not going to output the octree data, but I am going to comment all of this stuff out. Oh yeah, I guess you're right. We don't need to. So let's go ahead and remove the SKD couts. There we go. So this should be okay. Good. Okay, so let's go ahead and write this. Go over here. Do Control D and make. Error for I forgot an integer. Okay, let's go here. Now let's do make. Okay, so now we should have everything in pout.dat. Let's go ahead and open it up. And it is 510 lines, which is correct. So let's go ahead here and run a new plot. Now we're going to spot the first time step. So it's going to be splot pout.dat I0. Here's the very first time step. Now what I'm afraid is the very second time step is all going to be the same. So let's plot I1. Okay, good. So they did very slightly move. Let's go back to I0 and let's replot. Can I just put R? No, it has to be rep. Rep. Okay, so here you see the move, and we can see the move again just by plotting 2, 3, and 4. I don't know if there's a 5. Okay, so here you're seeing all of the particles kind of move closer together, following our gravity, right? So let's see if we can kind of follow one particle in particular. This guy moves closer and closer. And what's super cool about this, I don't know if I can zoom in any. Here, let me see. What's super cool about this guy over here, I don't know if you can see it where you're from, but you can see it start slowly and accelerate faster and faster. So every time step, we are seeing a clear accelerating pattern, which is great. That means that this is working perfectly fine. And I'm quite happy with that. Good, okay. So now, question is how we proceed from here. So one thing we need to do is implement more physical force guy. So let's do that. So before, what we did is we assumed that the particle acceleration was constant with every individual, how do I put this? We assumed that the particle acceleration was always constant. So what are we doing here? We're saying particle, so we're reading in some sort of particle, and we have some sort of time step. Okay, so this is within our loop that we have above. So remember how we had, here, let me just go up to it. We had one loop that was going through all of the particles and finding the new acceleration with RK search. And then we had all these other particles down here, each one being updated. So then we're updating all the particle positions. Now, what I might want to do is move that loop into RK4 itself. Because I have to kind of think about how we're going to do this next bit. What I think we might do is update the particle position. Yeah, so let's try this. Let's go down to the bottom here. And let me see. We have position 0 is the particle's initial position, which is fair enough. Then we say particle velocity and particle acceleration. Now, let me see. We want to change that acceleration. So what we might do is the following, and I don't know exactly the best way to do this. So let's just do this. Let me go up to the RK search. We're reading in the particle there, and we have the current node that we're going through. However, I have not read in the current node to RK4. Okay. So what we need to do is update the acceleration. The only way we have currently to update the acceleration is with the RK search algorithm. Or not algorithm, the RK search function. So now we have to write kind of a new function to update the acceleration here. So how are we going to do that? Well, it's basically going to be the RK search again, except reading in different parameters. So what we'll do is we'll read in a particle. I guess we'll read in a particle again. No, we're going to have to read in. I think we're definitely going to have to read in a node. There's no way to do this without reading in a node. So, let me see what we did up here. The particles do not move during the time step. I don't know what you mean by that, because in my opinion they do. So, the acceleration is obviously gmm over r squared, right? So what we do is we change the position here, right? So what we're doing is the position starts at 0, and then the next position is dependent on the previous velocity, right? So we are assuming we're here, and then here, and then here, right? So the position is changing, so the acceleration too must be changing, right? I mean, that's currently how I'm conceptualizing it, right? So for those who are not maybe following that logic, here, let me go here. Page, new page before. Okay. So we have, 1 second. We have a particle here. And a particle here. So you're saying we should just leave the acceleration constant? I mean, I'm okay with that. I mean, the difference is kind of minimal in the end. It doesn't really change that much. Okay, so we have the force of gravity affecting this guy and this guy, right? So force is equal to gravity times mass over r squared. With the RK4 algorithm, we have 4 different positions: P1, P2, P3, that was a B, P3, and P4, right? And so the idea then, or rather, you know, what I was thinking about was that every time these guys change position, this R value changes, which means that we have to change the force, right? So that means we have to change the acceleration, because force is equal to mass times acceleration. So the acceleration is based on the particle location. Let me see something. So Gustrom was saying this guy runs very slowly if we add like 1,000 particles. So let me see what happens if we do that for 5 time steps. If it's quite slow, we have to find ways to speed it up. So this is going to do nothing but slow it down, and I think it's going to be a minimal change in the end. So let's go into VI Barnes Hut .h, and what do we have here? Let's see, particle mass. Okay, so I guess I need to go up here, right, to the first, and let's change this to 1,000. Let's go over here, right quit. Everyone's saying, oh, 10K. So 10,000. Let's go over here. And let's run make. Did I write it? I did. Make. Okay. So give it a second to do its thing. I don't know. Oh, that wasn't so bad. Let's do 1,000,000. Let's go over here and make that. Okay. And give that guy a second to run. It'll probably take, I don't know. Oh, we should have timed it. But we didn't. Oh well. Okay. So let me do this then. I'm going to run a lot of particles. Now, obviously, we're outputting data, so that's going to be the slow part. Actually, I think what made it faster was this. So let's go back to 10,000. And let me do the octree output. I bet you that's slowing it down. Time make. I really think the octree output's what's taking so long. Also, couting probably took a while. No, that took no time at all. Huh. Okay, that's fine. Not sure. So let's go here to, again, let me do, that's 100,000. This would be 1,000,000. 10 million. Okay, now let's do time make. Okay, this should take a little while. Let's see, if it took about a second last time, this should take about 100 seconds. So it should take about a minute. I just want to check. Not a big deal. Now, of course, we can do a whole bunch of things here. Like Gusfriend said, we can increase theta. And what that does is that makes it so we do our approximation differently. So let's go into vi barnshut.h. And let's see, theta here is 0.5. 0.5 is a very typical number, but I think some people would change it to 1. I think in the original Barnes Hut paper. ZZ Hey? Yeah, so I just timed, I ran time make, and it just ran, yeah. You can time any command, and it will, it'll time that. No, I could put it into the make file. That's probably a little bit better. Okay. So, if we change theta to 1, basically what we're doing here is changing the way that we're approximating the system. Now, yeah, here, I think it was kind of obvious because we're doing time make. I need to get a quick sip of water. Sorry about that, guys. Okay, so now we have to think about different ways to work with this. One thing I want to think about is parallelization. Yeah, that's right. How are we going to split this up to work with all of my different processors? So for example, if I run top right now, you'll see that only one processor is running really that well. See this guy right up here, or something like that. Only one processor is running at a time is what I mean. What we can do is we can parallelize this. So we can use all 12 of my processors at once, and that'd be super nice. Question is, how do we do that? I'd like to use OpenMP just because I know how to use OpenMP and I don't want to get an MPI for this. However, I don't currently know the best way to do the parallelization. So let's go through and let's take a look. So we have the loop that's taking the most amount of time. Let me think. What are we able to parallelize? Well, let's go and let's see what we have here. 1 second, right quick. vi barnshut.cpp. Okay, and let's go down here real quick to, let's see, we have make octree, divide octree. Yeah, see, that's what I'm thinking too. But because it's recursive, I'm not sure exactly the best way to work with that. So let me see, octree output. That's fine. Particle output, force integrate, RK search. Okay. So we do auto particle root pvac. Okay. So if we put, where's RK search? RK search is down there. I think that's fine. Can you give my 500 subscribers? I don't know what you mean by that. I don't know what you want me to give your 500 subscribers. But whatever it is, maybe if it's something code related, I don't know. You can do both for the loops. Yeah, I think you might be right. Yeah, let's go ahead and implement that right now. We already have the fopenmp flag on the top. So let me go here, include barnshut.h. So I guess we'll just go into barnshut.h and add in fopenmp. Subbot? I don't know. I don't know. So in order to get subs on Twitch, you've got to be partnered with Twitch, right? So I suppose you're already partnered, which means you're already ahead of me. So there's not much I can do there. I think it's fopenmp. I think that's right. Okay, so let's see what happens. Oh, omp.h. Oh my gosh, you're totally right. So let's go to omp.h. Write that. Okay, so the Barnes Hut guy is still running. Maybe I was a little bit... Maybe I was a little bit overconfident with the Barnes Hut algorithm running 100 million particles. So let me go over here, right quit, go into barnshut.cpp. How many was I running? Let me check. 1, 2, 3, 1, 2, 3. I was running 10 million. Let's drop that down again. Write this, go over here, Control C. Yeah, it was taking, it would have finished probably any time now, I bet. Let's drop it back down to 1 million. 1, 2, 3, 1, 2, 3. Yeah, write this. Let me run that. And actually, let me go into the make file. And let me just do time this. There. And let's change this to dev null. Yeah, let's see. So I think it's this. 1 second. Dev null. Okay, now let's make that. Okay, so we should be timing it. Yeah. So give it a second to do its thing. I don't know how long this one will take. Oh, I did right, didn't I? Yeah, I did. I changed theta to 1, which changes the way we do our approximation. Obviously, as I said before, the higher the theta value is, the more approximate our values are. Now, one thing I want to point out. Yeah, one thing I want to point out here is we are... You're redirecting the timing data? Oh, oops. You're totally right about that. Let me do... Oh, no, I didn't. 39 seconds. Just remove the dev null. Yeah, let's see what happens. Let's do vi makefile. We can probably remove the dev null. Now let's do make. Command not found. What? Oh, it doesn't know what time is. What? It just knew what time was. Make. Alright, so now it knows what time is. Okay, 1 second, let me check something. I'm not exactly sure what's happening. So let's remove dev null from here. Right, quit. Make clean. Make. I swear, it knows what time is when I'm running, when I'm outputting a dev null, but for some reason it doesn't now. Okay. Screw it. It output the time when we were outputting the dev null. Let me do make file here. Let's run a quick test. Here, let's go ahead and do dev. Oh, must have caps lock on. Sorry about that. Dev null. Not exactly sure what's going on there, but we'll see. So now let's go ahead and what I'm going to do is I'm going to change the number of particles here. So let's go to barnshut.cpp. Let's change it to 100,000 so it runs a little bit quicker. Write this, go over here, and let's run make. Give it a second to do this thing. Should only take like, I don't know, yeah, 4 seconds. Now let's see what happens if we change theta. Right, quit. Barnshut.h. Let's change theta again to 0.5 and let's see what happens. Let's go to make. I just want to see if we're actually excluding any particles. I've got a feeling we might not be. 1 second. Okay, that one actually took a lot longer, which is fair enough. Yeah, that totally makes sense. Because as the theta value goes lower, we're taking into account more and more particles. Yeah, so that makes sense. Good. So if we change the theta value to, let's say, 0.001 or something, this should take into account all the particles, basically, all the particles. So let's go ahead and make that. And I just want to see something. I've got a feeling this is a very bad idea. Maybe I shouldn't have done that, but that's okay. So, give give this guy just a second to do his thing while we're implementing the parallelization stuff. And I just want to point something out, guys. I just ran with a theta value of 0.5, and it took 12 seconds to run. I ran with a theta value of 1, and it took 3 seconds to run. Now I'm running with a theta value of 0.001, which means we're basically taking into account all of the particles at all times, and it's taking forever. So I just want to point this out, that this might not run in the time that we're doing the OpenMP stuff. And the reason I'm pointing this out is simply because this is kind of the power of the Barnstad algorithm. You know, this is why, you know, it's used. Because as we're going through and we are doing our force integration, we're basically ignoring all of the particles that we don't need. So let me see, RK search here. Here's what I want. So before these for loops, I'm just going to very quickly put the following. Pragma, parallel 4. Yeah, there we are. You're downgrading from an... Well, yeah, so it's going from an n log n, which is what the RK4 was, to Pragma, an n squared algorithm. Parallel 4. It's just cool. I'm sorry. Okay, so that should be what we need. I need standard loops. Oh, yeah, fair enough. So here's what we're going to do. We're going to say for the following. So we're going to say for int I equals 0, I less than root pvec.size. Then we're going to do I plus I. It doesn't really matter in this case. So then we're going to say, instead of particle here, we're going to say root, and then root pointing to pvec of I. And that should be right. And I would do the same thing down here. So, we could probably change those to size t's, and it should still be okay, I think. Good. Let's go down here, do the same loop as we had before. In fact, why don't we just do this? Yanking the full line, pasting line underneath. Then we're going to change this particle to the following. Root pointing to pvec of I. Typo in the top for loop, which means typo in the bottom for loop too. 4, there we go. Let's remove this, and let's remove that. Okay, so obviously this guy is still running. Again, this is just kind of, I wanted to show you guys that we are clearly doing something with this Barnstad algorithm, and that's super useful. So let's go ahead and Control C here, write this. Now let me go into the Barnstad.h, and let's change our theta value back to 1. Just so we do some heavy approximations here. Write this, go over here, and let's run the make command one more time. Ignoring pragma parallel 4. 1 second. Isn't the loop faster if you don't do it this way? If you do it this way, for int I less than n. Maybe, yeah, let's see what happens. So let's go to, I don't know if it's any faster. So let's go into barnstad.cpp. And let's go back down. It's ignoring the pragma on parallel 4s, which means I'm doing something wrong with the parallelization, which is a bit of a pain. So let me see. Why? Pragma on parallel 4. Is that not right? Run quit. Vi. You use for in I equals vec.size. I minus minus. Yeah. Oh, I see what you're saying, because this way we're doing a vec.size every time. I see, yeah. Okay. 1 second, let me think. I'm going to very quickly look into some other code that we have where we do the parallelization, and I think that would be in archive. Let's see, md, daemon. Then I want to check daemon.cpp. Let me look for pragma. No, okay, apparently didn't. I thought we parallelized this code, but apparently I was wrong. Okay. What else do we have here? Daemon, md. Did we do it with piston? I was fairly certain that we parallelized something. Let's see. md.cpp. No, okay, maybe I'm wrong. What did we parallelize before? Let me cd, let me just ls a directory behind. Okay, so we have dmrg, fttd. Did we parallelize that? We must have parallelized that. So let's go into vi, fttd, invisible lens. And what else do we have here? fttd.cpp is probably what it is. fttd.cpp. Then let's see. Pragma. Here we are. Pragma on parallel 4. Oh. Huh. What did I write? I thought that's what I wrote. Let me go into barnshut.cpp. Go down to Pragma. Pragma on parallel 4. Am I missing something? I thought this would be super simple. Why are you not, 1 second. Ignoring. Yeah, I'm not sure. Okay, so let me think real quick. So, yeah, one thing is vec.size. The other thing is checking against 0 is faster than checking against an arbitrary integer. Sure, let's do that. So let's do, I thought, wait, let me go into the make file. Oh, holy crap. We don't have it active. 1 second. That was totally my bad, guys. I always run with the same standard set of flags, and OpenMP is usually up. For some reason, let me make this. Okay, now it made. And look at that. Whoa, guys, it went from 3 seconds to 1.75 seconds. It's parallelization. That's what you expect. Okay, so now let's... Okay, so now let's go ahead and change those loops. Maybe they are faster. Let's do it. So we're going to say size t I equals... yeah, sure. Size t I equals root pointing to pvec dot size. Then we're going to say I greater than, or I minus, whatever, I greater than 0. Or I guess not equal to 0. And then minus I. Oh, my bad, guys. I wonder if we'll actually see any difference. Maybe, I'm not sure. Let's see. Change this. There. I minus greater than 0. Oh, is that really... Okay, let's do it. I minus not equal 0. I minus not equal 0. Sure, let's do it. Write this, go over here, make. Okay, so it's having some problems with these guys. I guess you still need the semicolon. Yep. Make. So what do we have here? Missing increment expression. 1 second. It doesn't like it without that last expression. Let's see, root pvec.size. Vec.size. We have root pvec.size. That should be okay. Missing increment expression. I mean, I know it worked before with the I, or it should work before with the I minus. Let me see. So I'm not familiar with doing this without an increment. I always have like the I++ or something at the end. So let's see. Missing increment expression. I'm just going to do it the other way because again, I'm not sure. Let me just run it with minus I. Again, I don't think it matters here if it's post or pre-increment. Let's go over here and let's make that. Invalid controlling predicate. Okay. 1 second. Gotta think here. Invalid. I've actually never run into this error before. So 4, size t, I equals 0. This obviously has the same problem in both loops. What if we just go up here? Oh, 1 second. And we say... Wait, why does it matter in this case? Size t I equals vec.size. Yeah. While Can we still do pragma on parallel 4 for that? So I guess we just go up here. No. So we have to do a parallelization. Wait, 1 second. Size t I equals 0 while I minus minus. One second. Okay, so here's what I'm gonna do. Let me go up here. Let me just say size t. Maybe. Let me just. Well, I'm just gonna change it back to what it was before, because at least that one seemed to work. So equals, what do I want here? I equals root pointing to pvec dot size I plus plus whatever. Let's yank that line, go over here, remove this line, paste that. Now let's go ahead and make that. Oh, it still doesn't like that. On parallel 4 size t I equals 0, less than, obviously. Whoa, what was I doing? 4 size t I equals 0, I less than. Here, 4 size t I equals, not sure what happened there. Let's go ahead and yank this, paste that, there. Write this, go here, make. Okay, that doesn't seem to run, and it should take 1.8 seconds. Let me run it one more time, just to check something. Make clean. Make. They should all run about the same time. Now let me increase the number of particles by a significant number, or we could just increase theta. Yeah, let's increase theta. So let's go to barnshut.h. Guys, if you're just coming in or you have any questions, feel free to let me know. Because again, I realize coming into the middle of a programming stream, it's kind of difficult to really follow everything that's going on. So let me run top. Let me try going over here. Didn't know that. Thanks. So let's also increase the number of particles over here to whatever we have. That's fine. I'm gonna have top up so you guys can see that my processor is doing something, and I will increase the size here. Now let's run over here. Let's write this. Now let's run make, and let me pull up top. Okay, so it should be, maybe not, maybe. There we are, parallelization. Boom. So that must have been all initialization, and then we're running the parallelization here. Okay, I see. So now all the processes are running. Let me know if you guys see any lag or anything like that. There might be some sort of lag in my voice or something like that. So if you guys see anything, let me know. And there we go. That looks like we should be. Oh, we must be outputting or something. Yeah, so that must have been the first time step. Oh, never mind. We're good. We're done. Okay. So you just saw that we were using all 12 of my cores. Now, let me run new plot. And I just want to try something. I want to plot I0. Just to show you how many particles we're running. This is probably a very bad idea. Yeah, let's see what happens. So, if you remember, just a few minutes ago, it's 6 cores hyper-threaded. Okay, so if you remember from just a little while ago, we were running with like 100 particles or something like that. Now we're running with 100,000 particles, I think. So this is how many particles we're running with. It's actually, it's not possible. I cannot tell what's happening right here. We could change the size of the particles to be much smaller, I suppose. But that's kind of where we're at right now. Okay, so what do we have? What are we currently writing out? We are writing out the particle positions, which is good. We're writing out, let me see. I guess everything we need. Let me go ahead and run with a smaller number of particles. Let's say just 1,000. And let's see what that looks like right here. Control D, and let's make that. Okay. Theta should be at 1.5. So let's go to new plot. Plot alpha.I0. So here we have all the particles starting, but even here, there are probably too many particles to really get a good physical picture of what's happening. So instead, let me just change this to 2. Control D, make. Okay, so we've done 5 time steps with 2. Go over here. Bring this down here. Okay, we have our 2 particles here and there. Let's run a couple different time steps. So now let's do replot. 1. Oh, maybe they're too far away. 2. Yeah, they're too far away. 3. Yeah, so they're so far away that they aren't even counting each other as particles. Dang it. Let me just shoot. Let me go barnset.h. Let's change theta to 0.0 something. Control Z, make. Okay, now let's try it. New plot. Plot. Oh. Plot. Initial 2 particles. I think they're still too far away. Let's do 2. Yeah, they're too far away. Okay, so let's change this again to 100 particles. And let's change it back to theta 0.5. This is my bad, guys. So let's go to .cpp. Change this to 100. Maybe this'll give us what we want. I just want to see a small scale test, just so I can kind of physically check what's happening. Okay, so now we're gonna run new plot. Plot. Here we are. Here's all of our particles again. We've already seen this plot before. This is what we were running before. Maybe if we ran it with 10, it would work. Not sure. Okay, so let's try 1. So here we see some of the particles moving forward. Let's do 2. Yeah, there we go. 3. Faraway particles should still count. Faraway particles should still count if the theta is super duper small. So here's what we should try then. Control D. Let me try 2 particles again. Let's go over here. And let's go into barnshut.h. And let's change theta to actually equal 0 in this case. Make. Let's run new plot. Plot I0. I4. Dang, why aren't they counting? I0? Because you're totally right, Guster, and they should. They should be moving at least a little bit. But they clearly are not. Okay. Only if they are replaced by their node center of mass. Okay, so let me think here. You know, one thing that we failed to do every time step that we need to do is actually update our octree. Which goes back to my point that we never set the acceleration for particles that do not fall within theta. I'm not sure. The acceleration for those particles should be 0. So I think those are set. Right? Let me think. Okay, we have to do one more thing before moving on to the visualization, guys. At least. But let me think about this. So we have to figure out why those 2 particles are not currently interacting with each other. That's one big thing we need to fix. Another big thing we need to fix is that we actually do need to update the octree every time step to change with all the particles as they move about. So let me see. What do we have here? We have run quit. Let's go down to RK search. I just want to let you know that I love your stream. Thanks, man. I am a physics student myself as well, and I also want to do physical simulations in the future. So from now on, I will watch you every evening. That's great, man. I really appreciate it. And again, let me know if you have any questions, comments, concerns, anything like that. Like, I'm not here claiming that I know what I'm doing. I'm here claiming that we can learn what we're supposed to be doing together type of thing. So, you know, if you think I'm doing something wrong, let me know, and we can totally talk about it, kind of like what we're doing right now. Okay, so we're at RK search. Let me see what happens. So we just paralyzed everything. There's one thing I need to do every time step, which I'm failing to do at this point. And it is going to slow down the simulation significantly. Let me go up to the top real quick. Actually, no, let me open it up over here. vi barns hut.h. If the theta equals 0, theta 2 less than or equal to theta is always false. Theta 2 less than or equal to, yes. 4. Oh, I see what you're saying. Yeah, 1 second. Let me think about that. Let me go down here to our functions. Vector particle, where we are. Make octree, current node. Make occhild. What do I want? I want divide octree. That's what I want. Make octree. There we go. Let me see. What do we have here? Node star make octree. Let me go up to the top. And maybe there's a better way to do this. Maybe there's a way to update the octree instead. Where do we do this? Make octree pvec. Is that different than how I had it before? I feel like this is a little bit different. Maybe it's not. Maybe that's exactly right. Okay. So we have to think of a way to update the octree. And there has to be an efficient way to do it. I haven't quite figured that one out. So let's go here. Okay. Let me see. Where are we? We were at the RK search function. So if theta 2 is less than or equal to theta, then we change that. Oh, I see what you're saying. Yeah, I totally see what you're saying now. So this is because yeah, it's different. Also move the initial creation to the node as well. Okay, so we got a couple things we need to change here. So particle acceleration plus equals t. What was I saying? So before I was saying that we only change the particle's location. One second. Oh, I see the problem here. Yep. Okay, so I have to think about this a little bit. Here's the current issue. Let's go over here, page, new page before. Lots of things to think about. This might actually take a little bit longer than I thought. I was expecting to finish all of this kind of stuff today, but we might have to wait a little bit longer. Hey Slayerdar, thanks for coming in, man. Okay. Where's my pen? Found it. I use a drawing tablet. An amazing idea for you to implement in one of your streams? Yeah, let me know. I'm totally interested. So let's see. Right now we have... Okay, let's just draw a box with two particles in it. Here's our box. Here is our box. And here's our two particles. Here and here. Okay. Make your own reenactment of Deep Blue beating Kasparov in a game of chess. That takes a lot of time, man. I mean, we'd have to go into a whole bunch of AI stuff, which I don't know anything about. But that said, I would like to do some machine learning on the challenge, so on the channel. So we're not so far off. We'll get there, something like it eventually. But it's maybe it's not so bad. Yeah, I'll have to look into that. Actually, I have no idea how much work is involved with that. We'll see. But definitely something to keep in mind. And definitely something that we'll do something near in the near future. So we'll see. Okay, so let's say we have these two particles very far apart. Okay. Honestly, machine learning's really cool. I've only done it once or twice and I'm really bad at it. That's all I know. So the force that's enacting on these guys is force is equal to G m over r squared m1 m2. Sure. Okay. So we have something that's moving this guy this way and something that's moving this guy this way. Here's how we're currently saying, how do I put this? Here's how we're currently checking to see whether the particle should have its acceleration updated. If the current node that we're on has a theta value, where theta is going to be equal to, again, this distance here, s, and this distance here, d. Theta is equal to s over d. If this theta value is less than the theta threshold, let's do theta thresh, then we update it. And I did this so that we didn't take into account center of masses that were not the center of masses that we wanted to take into account. Does that make sense? So let's say we have a cluster of particles here. Something like this. But our particle only sees one big particle instead, right? Or the other way around. Let's say we have, let's say our particle actually sees the following. So instead of one big particle, our particle sees kind of like 4 smaller particles, something like this. In this case, there is a center of mass here in the center, and I did not want it to take into account that center of mass. So I said, as soon as we get under our theta value, we take the center of mass into account, and we don't deal with anything underneath that node. If that makes sense. So like here's our node. So we have a node here, 1, 2, 3, 4. And if we wanted to take into account 1, 2, 3, 4, we should not take into account this node up here. We should only take into account these nodes down here. So I don't currently know how to set this theta value to do this the way that we want it to do it. So maybe what we should do is we should say, we should have some sort of condition that allows us to check all of the particles appropriately. Not sure what that is. So let's take a look at what we have here. Or Gustorn can just code it up and then we just follow what he says. That's how it ends up going anyway. So let's take a look. Open link. Let's go over here. Auto size current p vector. If size less than or equal to box threshold. Okay. Current p vector dot size. Okay, for constant auto p, current p vector, acceleration for each particle. Auto size is equal to current p vector dot size. Sure. Okay. So we have. Yeah. I think I see what you're saying. So what we need to do then is the following. Basically, for constant auto p, current p vector. So we're going through all the particles in each p vector. Then we return. If size t. And where do we define box threshold? This box threshold has to be an integer. So let me see. Here's what I'll do. I'll go over here, and let's take a look here. So we have the else branch for auto child and current children. We do an RK search. If theta is greater than theta, then we keep going down. So I guess we need maybe something like this. How about else if maybe how do we do this? If there are no children node. Yeah, so how about if current pointing to pvec dot size equals 1. So this means that we're already in a leaf node. Oh, what am I doing with parentheses here? That was wrong. Open. What if we do something like this? Here. So that we make a special case. Ship it Hollis Ballas. Is this homework or just a hobby? It's just a hobby, man. Someone who, if we are in a leaf node. Actually, I don't think anyone's ever come in here asking if it's homework. Okay. If we're in a leaf node, maybe something like this should do it. So this is saying, not sure. But let's just see what happens. Let's write this, go over here, right quit, make. Current pvec.size equals 1. I forgot parentheses. Let me go here, add in some parentheses there. Write this over here. What else did I forget to do? I did nobody once. Oh, I did nbody once, but never did mesh or Barnes Hut. Yeah, so nbody without Barnes Hut is going to be usually an n-squared type of thing, which we've done before, actually. We did it with the molecular dynamics code before. However, that should do it. I wrote it with box threshold because it's more generic that way. Yeah, we could read in a box threshold. We'll leave it at this for now. Let's see what happens. Let's go to right. Let me go over to the top and let's change this. We have 2 particles. Let's see what happens if we make it. We should just see 2 particles moving together. So we're going to do new plot. Plot I0. This is where they initially start. And now let's do replot I4. Okay. Have these guys changed locations? Yeah, but very, very, by a very small amount. That's okay. Is Barnhut's nlog in? Yeah, nlog and what you said. Okay, so let me go up here. Let me go into vi pout.dat. Okay, 3.05709 to 3.06065. It's working. Yeah. Okay. That's what I wanted to see. We're seeing very small acceleration because we're super far away. That's perfectly fine. Now, there was one more thing that was mentioned in chat, but I totally forgot what it was that needed to be updated. Oh, never mind. This is something that I mentioned. We need to make the octree again every time. So let's go ahead and right quit. Now, let's talk about the octree real quick. The octree is our ability to physically approximate our system, right? So, in order to get an appropriate physical approximation every time step, I don't see a way to do it without modifying the octree. Now, there is... Oh yeah, we can do more than 4 iterations. Let's let this run for... Let's say... because it's only 2 particles, let's just let it run for 100 iterations. And let's go ahead and make. It shouldn't take that long. Yeah, literally half a second. And we'll do pout.dat. And you can see it goes from 0.262 to 37.64. So let's just watch this as it goes. So let's go ahead and quit here. Run new plot. We'll plot the initial particles here. Let's make it a little bit bigger. Do you rebuild the tree each iteration? What happens when a particle moves? So I don't know how much you've been following, because I think you just came in, but I'm not sure. But every time a particle moves, its physical location obviously changes, and the octree, which is, again, our physical representation of that location, needs to be modified for that movement. Now, there's probably a way. There is probably a way to simply modify, instead of rebuilding the octree, just to modify the octree we already have. For some reason, I didn't even think about that until now. Well, I thought about it, but it just was kind of in the back of my mind. So that's something we need to think about. Shipit, are you familiar with how octrees work? Because we can talk about that too if we need to. So let's just plot R5, okay? So at R5, we see very small movement of the particles, and I'm just going to confine it to this plane, okay? Now, if we go to R, let's say 10, we see them moving even closer together. R, let's do 50. Here, oh, let's try this again. So let's do plotting these guys. We're gonna do R5. There we go. Then we're gonna do 10. Let's do 20. Here we are. So here you can see the particles coming closer and closer together along this line. So here they're pretty dang similar, pretty close together. Okay. Now, if we do R30, you'll see that they come past each other, right? So now they've shot all the way over here. And if we keep going out, this is kind of neat. R40. These guys are way out here. And look at the order of magnitude here. We were from a box from 0.5 to 0.5, so we were in here. Now we're in a box that's 2 to -2. Do it again, and you'll see that we are going to be in, well, basically 6 and 6. Keep going. Basically, by the time we get to 100, we are in, oh, maybe there isn't 100. Maybe it's 99. We're in a box of basically 40-40, where our initial particles are all in here. which is neat. It means that we're accelerating and everything seems fine. So now let me think. One thing I have to think about here is how these guys are accelerating. It should be, after some point, they feel mutual forces to come back together, right? So it should be that they have some acceleration outward from when they were together, but they should generally want to, they should kind of come back together at some point. But here they're not coming back together. So let me try changing a couple of different things. Let's try changing the box size, or changing our gravitational constant. Let's change the box size to make it a little bit smaller, so they're a little bit closer together to start. So where are we? Which integrator are you using, or is it forward user? We are using actually RK4, so Runga-Kutta. We might change it a little bit later, but just RK4 is one of those that's pretty easy to work with. Don't have theta. One second, doesn't theta have to be 0 for that? Oh no, because we just changed things. So what we just did is we made it so that if there is only one particle in the box that we're checking our theta against, it will automatically use that particle. So we just modified it to so that we don't have to worry about theta in the same way. So here, I'll show you what we just did, because that's super confusing and I'm not doing a very good job of describing it. So every time step we go through, we check our nodes and we say, okay, what is the theta of this node? What is its distance versus its radius? Or radius versus distance, whatever. Then we check it against our theta that we have behind it. And we say, if there's only one particle in the box, we automatically take into account that force. So this just makes it so it's a little bit easier to deal with. Okay, so now let me go up to where we're randomly putting in the particles, and let's lower the box size. So they're literally right next to each other. Let's see, double half box length times 0.5. Where are we here? Box length is what we want to change. Create random distribution. Where are we? Random distribution 1.0. That's currently what we're working with. Let's change this to 0.1. Let's go over here, Control D, make. Okay, now let's run new plot, and let's plot just the very first time step. So here we are initially. You'll note that they're much, much closer. Now, let's see what happens when we plot 99. Okay, these are super far out. That's not making it easier to work with things. It's literally needed for the algorithm to function properly. Yes, that is true. Sorry about that. Let me think. I'm doing something really stupid here. What am I trying to see? Without that line, only particles that fall outside of theta are counted. Yeah, that's true. Let me think here. I have to think about, what are we expecting to see physically? So we see these two particles, they're coming together, and let's give these guys a velocity. Wait a minute. Maybe this is physical. Maybe I'm just being an idiot. So we have a force that's GMM over r squared. The closer they are together, the higher the force is, right? So if they're super close together, we're expecting to see a super high force going this direction, right? So towards the particle. Now, because we are not allowing the particles to collide, what will basically happen is they phase through each other with an incredibly high force going in this direction, right? So they move that way, very far away. And then the force acting on them to bring them back together is always going to be less than the force that they had when they were together to begin with. So maybe this is correct. Maybe they are supposed to fly off like that. I'm not sure, actually. I have to kind of think about that one. So let's change our force then. So before we have GMM over r squared, which should be Hooke's law, right? What is Hooke's law? Oh, Hooke's law is kx. Negative kx. So let's change it. We are not smoothing the force, we're just not taking collisions into account. So what we're doing here is we have not, they face through each other. Yeah, you're right. We're just not taking collisions into account. That's it. So what do we have here? We have the Oct children. That's fine. Particle output. What do I need to do here? Force integrate. What am I looking for? Dagnabbit, I forgot. I was looking for, let's see, we had the particles. Oh, I know. We want to go to force integrate. And actually we want to go here. And I want to change inverse R just to length of D. This is not physical at all. But let me just see what happens. So we're going to run make. And now we're going to run new plot. Plot the initial particle's location. Here they are here. Now, let me think. We should see negative kx squared is what I'm looking for. But this is probably incorrect. 99. They didn't move at all. Dang it. I don't know what I was trying to do there then. Let's do 1 over again. Because we know that this is at least something physical. Yeah, I'm going to have to think about this a little bit more. Sorry about that, guys. But at least first approximation seems okay, right? First approximation is that we have... yeah, should be okay. Okay, so now we have to think about things a little bit more. What are we doing with this octree? Let's go here, page, new page before. We've got about 20 minutes left before I end the stream for today. So let me just very quickly go through and talk about the octree, and let's see if we can think of a way to regenerate our octree without remaking it every time step. So let's go and let's draw what we have. So if we have a box, here we have here. This box is our root node. Let's say we have a whole bunch of particles in it. Something like this. Yeah, we can rebuild it every time step. The thing is, we're not going to see much of a difference. Right, so right now, yeah, it's going to be very hard to check to see. I guess we could create a test case. Anyway, here's what we're doing. Every time step we're going through and we're creating a new tree, right? Something like this. I don't know where to draw this line. Something like that should be okay. So we'll do here, there, here, there, here, there, here, there. Forgive me, I'm really bad at this. And here and there. Okay, so here's our octree. The wobbliest octree of them all. Let me change this real quick. So this needs to go here, and that needs to go there. Something like this. Here's our octree. Next time step, you could imagine that we have a particle here, move into this box here, or worse, move into this box over here. Yeah, let's just rebuild it every time step, and then we'll go from there. Yeah. I mean, rebuilding it every time step is the most general way to do this, I think. So we do an RK4 for every time step. If you imagine a particle moving across the middle, you're going to have to go back to the root node. Yeah, again, regenerating the entire octree is the most general way to run this simulation. I'm just wondering if there's another way to do it. Anyway, that's fine. Also, it will make it less efficient. Okay, let's just go down here and let's just do it. So we already have our make octree, we're reading in root. So let's just do make octree root equals make octree with particle vector. pvec. Okay, so we've updated the particle vector, and then we did create a new octree. Yeah, we could. I haven't used gprof in a while. In fact, is it even gprof for C++? I know it's for Customer doesn't like that. This is more efficient, much faster. Update. Do it in the outer loop. Let's do 1 second. Open link. Do it in the outer loop. I see. So you want me to do it. Wait, well, why is it bad to put it in there? Yeah, perf. Perf is what I was looking for. So let's see, force integrate, and then you want me to do... Oh, it's actually divide octree anyway. This is Linux, yep. So let me see, divide octree root 1? 1 second, what is the 1 for? Oh, 1 must be the box length. Let me go over here, Control D. Let me go over here to vi barnes hut.h. Let me go to divide octree. Node current. Oh, box threshold. Box threshold. 1 second. I don't remember having a box threshold. Let me go down to box threshold. Here. Oh, I see. So you could potentially have... Okay, that's fair enough. Sure. Okay, so we read in root. And let's see, what do we have here? We read in root. Node root equals make octree and divide octree at the beginning of the for loop. Wait, let me see. So, node root is equal to make octree, and then you want me to divide the octree at the beginning of every for loop. Sure, fair enough. So let's go down here. Let's do just that. Divide octree. Root 1. Whoever that is, thanks. I appreciate that. I don't know who it is though. PMST, Pacific. Wait, what time zone is that? Thanks. Okay, so divide octree root 1. Let me see, Guster, and remove the octree creation before the root. Good, so I think this is right? This is what you want. Let's do it. So, let's go down here. DD. Should be okay. Let me go ahead and run this. I've got a feeling I'm doing something majorly wrong here. Okay, so that didn't really slow it down that much. But we only have 2 particles. Let's change this to 1000 again. Let's go over here, make. Again, still pretty good. I need make octree as well. Okay, so I guess then we do this. We'll say root equals make octree of, what do I want? pvec. So we're going to want root pointing to pvec. So I guess what we need to do then, not a big deal, man. Let's do this. Let's put this at the end of every time step. Well, no. I'm not using what right now? Oh, is this in your vec.h? So ship it. Basically what happens is I code something up and it breaks and then Gustrun fixes it. That happens like almost every day. I'll be honest, I'm not the most proficient coder. So it always ends up being that there's something more efficient or something I could do. And I definitely encourage anyone watching this channel to send me pull requests, do whatever you want. That's perfectly fine. I have no problems with that. Okay, so what do we have here? Root is make octree root pvec. I'm noticing you're compiling with OpenGL. Do you have some sort of live visualization or just new plot thing? I've also used relative distance by sector, can't remember the name. Algorithm basically starts, updates objects by tracking nodes closest to the subdivided space. That's much harder to get working. Okay, let me look at Happy Little Rats thing. Ship it. We will eventually move on to OpenGL, probably starting tomorrow. Truth is, I'm very bad with OpenGL. I'm just getting started with that. So we will move on to that and go from there. James is so hot. What language is this? We are using C++ right now. And yeah, we'll be continuing using C++ for most of this simulation. In fact, if you go to github.com, you'll see that you'll see that we use predominantly C++, but there is a little bit of other languages in there. Let's take a look at what you've got then. So we have a study box 2D bullet. Let's see. Okay, so I'm seeing what's happening here is we have... Yeah, we'll see what happens. The N-body simulator should be pretty easy, I think, because we have a position for each of the spheres to put in. Should be relatively straightforward. And we'll see how it goes. Okay. I see. I mean, I've never used Java. It might be more modern. I think Gustorn and a few other people have significant reservations towards Java, but that's okay. So what do we have here? Underlying data structure ought to be a huge array of nodes. Fair enough. What do we have here? The node of the AABB tree can be carefully constructed to take up minimal space, as nodes are always in one of two states, branches and leaves. Since nodes are stored in an array, this allows... Okay, so this is something I'm going to have to look into, I think, later. It's not something I can do right now. However, it's definitely something we need to keep in mind. It's been pretty standard in physics engines in mid-2000. 1 second. Algorithm that basically sorts... Let me see. For compute-bound stuff like this, you probably want to use C++ or lower level. Gustorn for games, at least. Yeah, okay. So, let me see. Are we doing this right? I've got a feeling... you might not... Obviously, you're asking Gustorn, but yeah, Python is a pretty good language to start with, I would say. It's got great library support. Okay. So, we've got an issue here. Let me see. We're reading in a p vector. P output, particle output. Root will change. Yeah, so let me see. What does make octree do? Let me go down and take a look. Make octree. Here. Let's go down to it down here. Okay, so this basically gives us... What's the gravitational constant set to? This time step might be a little high. The gravitational... It's set to what it's supposed to be. It's G, so it's Barnes Hut. Dot H. So 1 times 10 to the negative 11th. Time step... Wait, what are you saying? Yeah, the time step might be high. That's not what I'm worried about right now. Right now I'm just worried about doing some simple test cases. Times 10 to the negative 11th is what it is. Yeah, right here. So we'd want the time step to be a little bit smaller than that, I think. Okay, let me see. Make octree, basically, what does it do? We have, let's see, root pvec reserve pvec.size. Yeah, okay, that's fine. So this is just creating a new octree. Root pushback particles. Wait, Gustorn, why do you want to make octree every time? Isn't it simply enough to redivide the octree? Let me see. So we have divide octree in there. And let me see. We go to root. Yeah. Oh, because the p vector has changed. I see. Because the p vector has changed, we have to remake it. Yep, you're set. Fair enough. Okay, so what we'll do is we will set it initially. And then what I would like to do is down here, I want to put these 2 lines. And you could do this a number of ways. I think this is good. Right here, go over here, right and quit, and let's make it. Root pvec, make octree. Initialization reference type std vector particle, expression type std particle star. 1 second, let me think. You just see set pvec and redivide. Let me see. Invalid type initialization of reference. So we have an issue here. We're reading in a pvec star. So vector particle star. So vector pointers. But what we need is a vector particles to make the octree. Yeah, okay. So what do we need to do there? Again, if we remove this make octree, it'll work just fine. Make. Yeah, totally works just fine. Okay, so now what we need to do is check actually the Octree output every time anyway. Just to see what's happening there. Octree actually updates PVEC, the original. Let me see. Divide Octree there. Wait. I don't want to be leaking very much memory. So let's see what we have here. Let's go here. Remove root. Or do this. I have to think about how to do this though. Because right now make Octree reads in a vector of particles. But I suppose we could make another command that reads in a vector of particle stars and goes from there. 1 second. We have make Octree root PVEC. Force integrate should be fine. Man, my brain is just shot right now. I can't think about anything. I apologize for that. So again, I think this will work. No, let me think. Why are we leaking memory though? That is because I'm actually really bad with memory allocation. Let's think. So root make Octree root pointing to PVEC. So we have to remake the Octree. Is there a way to do this appropriately? I can't think of how to do it. So let's go down and let me look at divide Octree again. Here. Let's see, node, current, size t, box threshold. Do you ever tear down the tree? No. Not unless we remake the Octree. Okay, so here's what I'm going to do, guys. For now, I'm going to leave the code right here, as it is. For some reason, I'm just not able to think appropriately right now. So let's go up to the notes and let's add things that we need to change. So all particles drift into a plane. That one wasn't quite fixed. Change particles, particle stars. That one was fixed. Okay. So what do we need to do here? We need to think about how we're going to regenerate. Think about regenerating Octree every time step. Now, again, happy little rat gave a link. So here's what I'm going to do. I misspelled little. Let's go to end. And I'm going to put a very quick colon and put this link in there. And this is something I'll be looking at today. No, they don't. Well, they don't anymore. So let me see what happens to this. 1 second. Let me go to the start. Add a thing there. That was something I didn't check, but we can check it really quick. So let's go to force integrate. Let's increase the number of time steps here to a large number. Let's make it. Now we are outputting every time step, which may be a mistake. If you add this at the end of the for loop, it should tear down the tree. Tree traversal post order root. Okay, end of the for loop. Okay, let me see. Which for loop? This for loop right here? Oh, I see. Okay. And do node root equals make Octree PVEC at the beginning of the loop. PVEC. The issue is that we don't have PVEC. I think. Oh, yes, we do. Okay, it's right there. Sure. But doesn't that reset the particles to start at the same spot? Because PVEC isn't changing. Here, so let me see. So you want to do node root. Node star root equals make Octree of PVEC. Here. Okay. So then we want... Is it changing? Oh, PVEC is what we're initially pointing to. I see, my bad. See, that was what I was confused about. Divide Octree. And we want to do root 1. Yeah, that was my bad. That was my bad. You're totally right. I was not thinking. Let's put a dot here. Okay. Does Octree remember PVEC then? We are pointing to it. So, in a way, yeah. So we're going to remove this, remove that. And what you want to do is add in the following. So after force integrate, add in traverse, post order, which I didn't know we had, but apparently we do. Root, and then we destroy all the nodes. So let's do node, start, node. And then we go down here. Oh, I see what you're saying. 1 second. So we have to add in the function there. So we're going to say traversal post order. Read in the node star node. Oh, I see. This is a lambda function. So let's go here. There. And then we're just going to say delete node, which is about what you'd expect. Then we have to add in a... Sorry about that. I know I don't know how you're supposed to notate this. So now let's go over here and let's run new plot. Let's look at the very first time step. Here's where they all start. I guess we have too many particles. And now let's try 1,000. Oh, I guess 999. No usable data in this plot. How many time steps did I do? 99? Control D, VI, pout, .dat, G. Oh. Oh, well that's not right. Did I miss a semicolon? Yeah, let me just go ahead and do this. Run quit. Make, it'll tell me where I need a semicolon. No, it won't because I forgot to write it. Now let's make. Semicolon. There. Obviously because it's a function definition. Okay, now we'll make that. Oh, never mind. I did something stupid here. 1 second. Expected. Maybe it's here. Make. Okay, that one made. But it broke. Okay. So let me think. We currently have a segmentation fault happening, which means the traversal post order is not working right, which means I wrote it in wrong. And it's probably because there needs to be an additional, let me think. Delete node. Huh. 1 second. Let's go to the traversal post order then. Vi barnshut.h. And let me go to traversal. Traverse. Okay, traversal post order. And let's see what we got here. Template type name T. Traversal post order node current constant T function. So what are we reading in? We're reading in root and constant T function. I'm not sure what happens if we delete a null pointer. Okay, so here's what I'm gonna do. For now, guys, should, let me see, node. Where's node? Okay, so that's the destructor right there. Alright, I've got to think about this a little bit more on my own time. So let me go ahead and go here. Let me comment this out for now. Here. And there. Write this, go over here. Run quit, make it just to make sure it makes. And it does. It makes just fine. Okay. Nothing happens. Yeah. Okay, so let me go up here to the notes real quick, and let me add another quick note about this. Sorry about that. I'm kind of out of it. Happy little rat. Mention that. Okay. And let's see. So it works just fine if we don't do that. Remove the destructor from node. Vi. barnshut.h. Okay, so let's just go here and remove this guy. Okay, let me go up here. dd, oop, my bad, dd, write this. Now what do I want to do? I want to go over here, write this, change the number of time steps to be 100 instead of 100 or 10,000. Header file line 64. And 118. 1 second. Inline node. Oh, make. Okay, that one seems to work just fine. Let's go ahead and open up. What do I want to do? I want to open up pout.dat. Go down to the bottom here. Something weird is happening here in terms of spacing. I'm not exactly sure why. Steve the Steve, if traverse post order is a function template, how can you call it without, traverse post order node? That I'm actually not sure about. Let me check the function template. Let me see something here. How many particles we're running with? 1,000? Let's drop the number of particles to 100. Let's go over here, right quit, make. Yeah, sorry about that. So we made it. Now let's see, we should be running with 100 time steps. Let's go to pout.dat. Again, I'm not sure why we have so many empty lines down here. I don't know what that means. Also, we're losing particles. We are definitely losing particles. Yeah, we are definitely losing particles. That's what's happening. Where are the particles going? I don't know. But they're gone. Okay. So let's go up here. pvec is... Yeah. So let me go here. Particle output. Force integrate. Make. Root was not declared in the scope. Particle output. Make. Okay, so if we don't divide the octree every time, we're not losing particles. Okay. Here's what we're gonna do. I'm gonna write and quit this. I'm gonna write and quit this. We're gonna do get status dot. Okay. So this is what I'm gonna do, guys. It's 7:08 in the morning, which is about 10 minutes after the time that I typically end my stream. So what I'm going to do is I'm going to commit this to GitHub, what we currently have. Yes, octree currently stores a pointer to pvec. It's currently working without the division to the octree. So I'm going to commit this version. You guys can feel free to look at it and do whatever you want with it. No problems there. So git add. Did the make file change? Let me see. Yes, it did with OpenMP support. Oops. So let's do git add makefile barnsut.cpp barnsut.h. I could have done barnsut star, but that's okay. And then vector.h. And we're going to do git commit. And we will say adding. Ignore all of this. I apologize for how messy this is. We will say adding OpenMP support. And what else did we do today? I don't remember. Right over here. Git diff barnsut.cpp. Oh shoot. It's okay. And small physical changes. One last thing to note. Octree division not complete. Okay. Run quit. Make put. Git push. Origin master. And let me see. Quick before you leave, what are you using? OBS Studio. Yes, that's exactly what I'm using. In fact, it might not be OBS Studio. It might just be OBS. I don't know the difference between the two. You can use git diff cached to see stage diffs. Oh, fair enough. I will use that next time. So, I guess it's too late now. But guys, it is on GitHub now, so feel free to take a look at it if you want. I'll continue to look at it tomorrow. There's going to be some issues here and there, but I think we can fix it tomorrow. Then after that, we're going to be working on open GL stuff. So we'll be moving on to that. Anyway, guys, thank you so much for coming in. Have a great day, night, afternoon, morning, evening, whatever day it happens to be your time, whatever time it happens to be your... Have a great time, whatever time it happens to be your time, whatever. I will see you guys next time for the next episode of Simuleos, and hopefully we can get this working and move on to the OpenGL stuff. We'll see how it is. Thanks, James. ZZ Hate, I will see you around, and that's it. Bye, guys. Have a great time. See you around. Here's OBS, I guess, Studio, for the record. Ship it. I don't know. I don't know what it is. Anyway, see you guys. Bye.